What's that?
You got a word.
Yeah, me too. So yesterday I went back and showed you how to find the modulus of a complex number, how to add them, how to subtract them, how to multiply them. That should be pretty much in your sweet spot now. So today we have to talk about how to divide them. So division problems look something like this. A complex number being divided by another complex number. Yeah, this will come back to you, I think, pretty quick. So when I'm going to use air quotes here, when we divide, so honestly, what I finally figured out to say is we're not so much dividing the complex numbers as we are just fixing the situation. You're not allowed to leave things with square roots, like irrational things, in denominators of fractions. So more than being a division problem, this is like a Mr. Fix-It. What I'm doing is saying, you can't be in the bottom of this fraction, so I'm going to make you go away. And so I don't know if that makes any sense, but it feels a little to me less like actual division and more like I'm just following the rules of math to make the problem look the way it needs to. So here's the deal. We learned yesterday that if you multiply two certain types of complex numbers together, you get a real number. Does anyone by chance remember what that situation was? If I said to you, write me a problem with two complex numbers multiplied together so that the answer is just a regular number like 10. Good job. Thank you. Way to use those notes. That we want to use what are called complex conjugates. And so I say, like, okay, if my mission is to make 3 minus 2i not be imaginary, because it is, it's got that I component, it's a complex imaginary number. If I want it to go away, so to speak, then what I do is I multiply it by its conjugate, 3 plus 2i. Now, that's not legal. Like, you can't just take the bottom of a fraction and multiply it by something. It is, however, legal if you do it the same to the top of the fraction. So we're also going to take the top of the fraction and multiply it by the exact same thing as we did on the bottom. You learned that back in 4th grade. You can do whatever you want to a fraction, provided that you multiply or divide by the same amount on the top and bottom, right? So having said that, what happens now is the bottom becomes just a nice little handy dandy number. And the answer to the bottom is real quick 13. And how you do that super quick is when you have complex conjugates, you don't have to go through the whole thing that we're going to do on the top. The top's a bit of a pain. The bottom is just this. What's 3 times 3? 9. What's 2 times 2? What's 9 plus 4? Then the answer to the bottom is 13. And if you want to see why that is that way, I mean, feel free to multiply out those conjugates in the red parentheses on the bottom, and you'll actually see that, wow, I'll be darned, it 100% of the time that has to work with conjugates. It's just times, times, plus every time. You ignore the negatives, you ignore the i's, the whole shebang, okay? But again, that only works with conjugates. So, mission accomplished. What we have to do now is just work out the top. And the top is just the 4-step multiplication process. So I'll color code for your convenience. What's 5 times 3? Good. So 1 down, 3 to go. Now let's head around to the outside. And again, you start to skip these steps the more you practice, but I don't think I'm at a point where I should. So what's purple? So plus 10i. Okay. And now we're going to head across to green, and green is these two in the center. What's that? Minus 400. Good. And then we'll do yellow for the tail ends. And what's negative 4i times negative or positive 2i? Careful. Yeah, okay, so you were jumping ahead, right? So minus 8i squared, so just plus 8. Thank you. Anyone have any issues with that? So we're almost there. What we're going to do now is we're going to take the red and the yellow and we're going to put them together to make the real part of our answer. And we're going to have 23. And then we're going to put the purple and the green together to make the imaginary part. What's 10i minus 12i? And at this point, it feels like we should be able to say we're done. But oftentimes what happens is, and honestly, if you stopped here, I don't see anything wrong other than maybe you just wouldn't be following someone's directions. So like if it was Miss Barrett's class and she said, okay, express your answer as a complex number in standard form, then you'd go a step further and you would actually kind of subdivide it. So what you do is you take now this and it becomes the real part of your number like this. And then you take this and it becomes the imaginary part of your complex number. So minus 2/13 of I. When I taught you this in Algebra 2, I required you to go to here. I may or may not require that. Depends on like kind of contextually where we're at and what we're using this for. Okay. Does that ring any bells with you? Is that the process? I know it's been a while, a little bit longer for some of you, maybe. I don't know. The last thing on the to-do list for the day, and I could go over problems with you when we're done, but I wanted to remind you of the powers of I. Do you guys remember what I is? Good. So this is a great time to start taking some notes because this part can be really confusing for about 5 minutes. And then once it cracks open, you go easy peasy. Well, we all know that if you take I just in general, it equals the square root of -1. So let's expand on that a little bit and say, well, then I wonder what would I squared? No. It would be -1. Because when you square something that's already a square root, then the square root goes away and you just get the number inside. That right there, that one statement on the board, the second line down, is the foundation of what makes imaginary numbers so crazy. Said this yesterday. Holy crap, I just squared something and got a negative answer. Whoa. We're going to go deeper now. We're going to take and figure out I to the power of 3. And I to the power of 3, I think the most success I've had when I try to teach this to someone is to show you that what I to the third is actually a blend of two things that we already know. If I know I to the power of 2, and I know I to the power of 1, having made it this far in your math career, you of course know that that's the same as I to the third, right? So what's I to the power of 2? So this equals -1. We know that from a minute ago. And this is just I. So the answer to I to the third power is -I. And that leads us then to, I think, what will become our favorite. It's inevitably got to be our favorite because it just feels so sweet. But if we take I to the fourth power, how do you build I to the fourth? That's what I would do, right? And I would take an I squared and I would think of it as multiplied by another I squared because 2 plus 2 makes 4, right? And I love I squareds because they're so cool and easy. What is each of those I squareds? -1. So if I think of each of these as -1, what's -1 times -1? Right. Is this ringing some bells? What happens now is the pattern starts to repeat itself. And if we went through and kept doing this, you'd find that I to the fifth is the same as, here, let me switch colors. You would see that I to the fifth is the same as I to the first. And you would see that I to the sixth is the same as I squared. And you would see that I to the seventh is the same as I to the third. And you would see that I to the eighth is the same as I to the. And I could switch colors again, and we can now say that, oh, wait, so if I just keep going, so is this I to the ninth? Yes. Is this I to the 10th? Yes. Is this I to the 11th? And in the interest of not driving ourselves crazy, we would stop there. But the point is, how can I apply that knowledge then to something absolutely obscene like I to the 345th power? Because I certainly don't want to figure it out. In this case, divide by 4, remainder's 1. I think it's going to be just going to be I. What we want to do is we want to think about the remainder when we divide by 4. You would agree that this sequence has a length of 4, right? 1, 2, 3, 4. So we're going to do a little bit of modular arithmetic here, and we're going to take whatever the exponent is, and we're going to divide by 4. So think about, this is where I will lose you. You've been warned. Watch out. 30 seconds. Sit up straight. Listen carefully. Are you ready? I'm just trying to be straight with you and tell you, this is, if you're going to get lost, it's going to happen right now. I'm circling in yellow. What is the remain? Okay, I'm circling in red. What is the remainder when you divide 1 by 4? The remainder is 1. So we're going to call this the remainder is 1 row. Are you okay? Okay. Now, Follow, do you see where I'm moving my pen right here? Again, I'm obviously using red. If I take this number and I divide it by 4, 2 divided by 4, what's the remainder? So this is my remainder is 2 row. You probably see where I'm headed with this. Again, follow Mr. Penn right here. If you divide 3 by 4, what's the remainder? This is my remainder equals 3 row. Careful how you answer this question, because you're going to want to say something and then you're going to have to kick yourself if you do. What is the remainder when this 4 is divided by 4? 0. Good. It has no remainder because it's a multiple of 4. When you divide 4, 8, 12, 16, things like that by 4, you don't get a remainder. We do not have a remainder equals 4 row. There are 4 things that can happen when you divide by 4. You can get a remainder of 1, 2, 3, or no remainder. And why this is important is those red numbers off to the right just tell us where to go. So let's think about this. Take this problem at the bottom of the screen, 345. Right now, take 345 and divide it by 4. And your calculator can do this for you, right? It'll give you decimals, but if we know how to interpret them, when you type this into your calculator, if you have a calculator with you, grab it and feel free, participate. Take 345 and divide it by 4. Say it again. Is it a remainder of 3?
No.
I thought it was a remainder of 1.25. Thank you. So what I get is I get 88.25 or 86.25. What's key is not the 86. That just means I got to go 86 cycles through all this asinine stuff I just did. Well, 1 cycle, 2 cycles, 3 cycles. Heck with that. We throw all that. That's what modular math is all about, is throw away all the excess. Let's get to the end. That means that when we get to the 345th iteration of this process, we would be right here. I didn't write 4. You can't prove it. God, it's on recording. I'll go back and I'll contact some hacker and make them edit my video. Yes, it should be 0, of course. Here I'm telling you, before. So, anyways, what the remainder is it? Oh, I have to fix my days without incident back to 0. Make it through Tuesday. What a loser. So whatever remainder you get tells you just where to go attack the table. I mean, your answer is either going to be I, -1, -I, or 1. One of those things. So that's why I to the 345th power gives us a remainder of 1. 0.25 is the key, right? That's 1 out of 4. So the answer is I. Let's practice again. There's a decent chance right now that you're really, really confused and you may not want to say anything. So let's try again. Let's do I to the power of 34,522. So grab your calculator and type in 34,522 divided by 4. It'll always be 4 because the cycle is 4 long. It's not the number at the front that I'm interested in. Your decimal at the end is either going to be non-existent, meaning we got no remainder, or 0.25, or 0.5, or 0.75. It's a 0.5, right? And 0.5 is the same as 2 out of 4, which means we go to the remainder equals 2 row. And what is the value when the remainder is 2? -1. Just like that. Got it? You feel like you can do this? You want to go again? You sure? Well, I'm going to stop my recording, I guess, and maybe I'm going to pause it, and then I'm going to go fix my days without incident, because clearly I'm incapable of not making mistakes. I knew you'd ask. Why don't you just for the practice, to make sure we're good at it? Takes like, what, 5 seconds? Yeah. So in problem 1 on the back, we have this. And what we're going to do is we're going to multiply by the conjugate. So we're going to take the bottom and just change the verb in the middle. Don't change anything. If there's a sign in front, don't change it. Only change the verb in the middle. So we're going to multiply by 9 minus I. And then we're going to hit that same math problem on the top. Now the bottom, I kind of breezed past this, but I hope, you picked it up. You're all pretty good mathematicians here. The bottom is quick. It's just 82. Like you don't have to go through the whole process. You just go 9 times 9, 81. 1 times 1 is 1, 81 plus 1, bottom done. Now the top is not shortcutty. It's just what it is. You can get quicker, but it's still just a thing. So yes, we're going to get some pretty big numbers here on top. So when we do the 16 and 9, we get 144. And then when we do the 2 on the outside, we get minus 16i. And then when we do the 2 closest to the center, we get plus 180i. And then when you do the 2 in the back at the tail end, you get minus 20i squared, aka just plus 20. So if you're following along, if you have any questions, now would be a good time to ask. Otherwise, I'll just press on. So. All right, then. So it's time to take red and yellow, put them together, and you get 164. And then if you put purple and green together, you also get 164. But it's got an I with it. Yes, I want you to divide these up like your answers. I want you to do the splitsy thing, only because we should at least practice it to the point where if we have to do it at some point, then it's not like we have to relearn it. So we're gonna divvy it up from here, the double diagonal division, the DDD. If you slap it this way, go down like that, 164 and 82 reduced to 2. And then if you slap it down this way, going in the yellow direction, again, 164 divided by 82 is also 2. So we just get 2 plus 2i, like that.